Now that we introduced angular momentum, let's look at further the analogy between angular and linear momentum. In the case of linear momentum, one of the things that made it really useful quantity was because it was often conserved. What was the condition for linear momentum to be conserved? Well, that's dp dt equals 0, right? So p does not change with time, right? And dp over dt equals the external force. So if the external force equals 0, then there is no change in linear momentum. Let me write this down for your review. If F external equals 0, then P is equal to constant because dp dt is equal to 0. That was the conservation of linear momentum. Okay, what we have here is the torque theorem, which says external torque equals dl dt. That's the most general expression. So what's the condition for L, the angular momentum, to be conserved? Simple. dl dt is equal to 0, which means torque equal to 0. So if the external torque is equal to 0, then L is a constant. This is the so-called conservation of angular momentum. So we have so far studied 3 conservation laws. We have conservation of mechanical energy, we have conservation of linear momentum, and now we have a third one, conservation of angular momentum. These conservation laws are the crown jewels of physics, and we use them very, very often. They're extremely useful. And please make sure you understand the condition for each of them to be valid. So when you know when you can use it, when you cannot. Okay, what's the condition for linear momentum, for the mechanical energy to be conserved? Well, the condition is all forces doing work must be conservative. Okay, when you have friction and friction does work, then you cannot use conservation of mechanical energy because friction is not a conservative force. What is the condition for linear momentum to be conserved? Well, simple. No external force. Okay, then linear momentum is conserved. What's the condition for angular momentum to be conserved? No external torque. Okay, so is it true that the condition for torque being equal to 0 and force being equal to 0 are the same? Well, not necessarily. You know, sometimes, as we learned before, it is true that the force may not be 0, but the torque it produces can be 0. Yeah, this happens when the observation point is right on the axis through which the force acts, right? You know, the observation point lies on the line of action, right? So that torque is 0 for this particular observation point. So, you know, it is possible for us to look at a situation where the net force is not equal to 0 or even unknown, but the torque it provides is 0. And therefore, I don't even have to know what that force is. Because the torque is equal to 0, then I have conservation of angular momentum. This can be very useful because the conservation law, the nice thing about the conservation law is once you know for sure you can use it, you can use that to bypass everything in the middle. You just write down L initial equals L final. Okay, you don't have to know how it goes from initial to final, as long as you know for sure the external torque is equal to 0. And if you look at an object with uniform omega throughout its body, then you know how to write this L, right? It is just I omega, so it's I initial omega initial equals I final omega final. For example, let me rewrite it. I get omega final over omega initial equals to I initial over I final. Okay, this is an interesting observation. It explains a lot of things that you see in sports on TV. Okay, for example, you see figure skating, right? An ice dancer. When the figure skater is spinning on ice, he or she certainly has angular momentum, okay, because of rotational motion, right? And roughly speaking, you can treat the entire body to be an object with the same omega value. The body is deformable, okay? So I can change. But at one moment, omega is the same throughout the entire body. So the angular momentum is I times omega. How does the angular momentum change? It changes because there is an external torque. That torque is typically provided by the friction through the ice. And that friction can be pretty small. You know, that's why you do these incredible maneuvers on ice, because your virtually free of friction. So as a good approximation, at least for a short while, we say as the person spins, as the athlete spins, we say the angular momentum is pretty much conserved because the torque provided by friction is very little, because the friction itself is very small. Okay, so as you spin, how do you speed up? How do you make your spin faster? Well, you have seen them doing that, right? If you haven't done it yourself, at least you've seen people doing that. That is, they pull their arms closer to the torso, to the body, right? As they pull their arms closer, what happens to I? What happens to rotational inertia? Well, you are getting the mass closer to the axis of rotation, so I decreases. Okay, so as I decreases, omega must increase because I times omega remains the same, right? So you go from initial omega to final omega. Final omega is greater than initial omega because the final rotational inertia is less than the initial rotation inertia. Okay, so by pulling yourself in, okay, so initially, you know, you're spinning like this, okay? You're spinning like this. And then you pull your arms in, so you're now spinning like that. You go faster, okay? You can go faster than that, right? But of course, you can go backwards. How do you slow down? If you start with this position, you pull your arms down like that, you're increasing I, and therefore you're going to decrease F. That's how you slow down. So physics explains what's going on with the rotational motion. You can change omega by adjusting I, because angular momentum is conserved. The smaller the I value, the greater the omega value. As an example of conservation of angular momentum, let's look at this example. You know what a merry-go-round is, right? It's basically a large wooden platform, wooden disc, very large one, and it spins around a central axis. Okay, and you know, people can walk on it, and they can ride wooden horses, whatever. Let's simplify this wooden merry-go-round as a uniform, solid disc of mass m and radius r. Okay, mass m, radius r. So I know the rotational inertia about the center, I, O, is 1/2 m r squared. Let's say initially it is spinning at a angular velocity of omega naught. Okay, it is spinning like this. So the initial angular momentum, L, initial, is I, O, omega, O. At that moment, there is a child who stands at the very center. Let's neglect the body size of the child because he is standing right at the center. He does not really contribute significantly to the angular momentum of the system. Okay? Because the angular momentum is measured from here, and since he's right here, his own body rotational inertia is negligible compared with the rotational inertia of the disk. Now, let's say as the thing is spinning, the child walks out with at an arbitrary path. Okay, you can walk whatever you want, but he eventually lands at the edge of the merry-go-round. So he is here now. His mass is small m. As a result, what happens to the rotational speed? What happens to omega? Will omega still be equal to omega naught? Well, no. You know, by common sense, it's going to slow down, right? How much does it slow down? Well, you don't want to look at the details, how the child walks out, whether he slows down, speed up, what kind of detour does he take. That's too complicated. You know omega is going to change as he goes out, but what you really need to figure out is whether or not angular momentum is conserved. Because it is. If it is conserved, I can equate initial and final angular momentum. I don't have to know anything in between. What governs the conservation of angular momentum? An external force. External torque. Okay, there is of course a torque, there is a force of support provided at the hinge here. Do you worry about the torque provided that force though? You don't, because that force passes through the axis of rotation, therefore it has no lever arm about that axis, and therefore it does not provide any torque. Okay, so we conclude that you can use conservation of angular momentum from this initial state to that final state. Okay, initial to final. You know L initial equals L final. How do you write L final? L final is equal to I final times omega final. Okay, so I final equals what? Well, first you still have I naught. Okay, you still have this from the disk. And then the child now contributes right, more significantly to the rotational inertia, you can consider him as a point mass, mass m, a distance r from the center. How much does he contribute to rotational inertia? Isn't that mr squared? Mr squared, right? Okay, then what is omega? Well, L final equals I final omega, right? Let's call it omega final. So this is omega final. And by conservation of energy, these two should be the same. L initial equals L final. So immediately you know what omega final is. Okay, omega final is then equal to omega naught times this ratio of I naught over I final. And I can work this out. We can see what happens. You got omega naught here. And this is I naught, that's 1/2 mr squared. Okay, you divide this by I final, which is 1/2 mr squared, plus the mass of the child, small m, times r squared. That's the final answer. Now, of course, you can simplify this a little if you want to. Let's simplify this a little. See how much impact the child has to the rotational speed of the object. Okay, I'm going to multiply everything by 2, and then I'm going to divide every term by mr squared. M is the mass of the merry-go-round. So I have 1 here. Okay, here's 1 plus 2 mass of the child divided mass of the merry-go-round, and then times omega naught. It's less than omega naught for sure, because you have the bigger denominator than 1. But how much less? Well, it depends on the ratio of the mass of the child versus the platform. Okay, if the child has insignificant mass compared with the mass of the merry-go-round, this term is almost equal to 0, which means yes, it's going to slow down, but not by much. Okay, so this is an example of conservation of angular momentum. You can even look at a variation of this problem. Let's say the child, once he reaches here, he starts to walk. Okay, he starts to walk relative to the platform, so that his velocity, his angular speed, is not the same as the rest of the platform, because he walks forward. How do you figure? Suppose you know that he walks forward at, say, a relative speed of, say, 0.5 meter per second. Compared with the rest of the platform. How does that change the angular momentum, the angular speed of the platform? Well, we can look at that as well. Okay, even as he walks, he is part of the system, right? This is the child, okay? The child walks with a certain speed relative to the platform. Let's call it V1. Relative to the platform. The platform is turning, okay? The platform is turning. But on top of the turning velocity of the platform, the child walks forward with, say, 0.5 meter per second, which is called V1. The rest of the platform is going to slow down as a result, right? Because, that's common sense. It's going to slow down. The question is, what is omega equal to for the rest of the platform now? Okay, the child and the platform is one single system. The force that pushes the child forward from the platform, that is part of the internal force between the child and the platform, so that force does not provide any external torque. Therefore, we still have conservation of angular momentum for the child and the platform. The only thing is that now that the child has a different omega compared with the rest of the platform, we must treat him differently in a separate term from the rest. When you add the angular momentum of the child and the angular momentum of the platform, you should still get the same value as before. The total angular momentum for the whole thing. So L is still equal to I/O omega O. Okay, now that is initial value. The final value, you add them together, you still get this I/O omega O. But how is the final value calculated? Well, this is the center, right? This is R. For the child, make sure, okay, you want to observe the velocity of the child from an inertial frame of reference, not from accelerated frame, inertial frame. So you stand outside the platform, you watch the child. How fast is the child moving? Well, suppose you know the angular velocity of the rest of the platform, which is omega. Now that omega is not the same as the omega that we just calculated, okay, because the child is now moving forward. But suppose you know that, then if the child stood still, he would still be moving relative to a person standing outside, right? How much would he be moving? He would be moving with a forward velocity of omega times r, right? Omega times r. That is as if the child himself does not move relative to the platform. But the child does, okay? The child also moves forward relative to the platform with a speed v1. So what is his total speed measured from outside the platform? You add these two up, right? So the child actually is walking with a speed of v1 plus omega r. v1 plus omega r, okay? And here is the reference point to calculate the angular momentum of the child. Think of the child as a point mass m, moving with a velocity this way, v1 plus omega r. Okay, first of all, by definition is r cross p. P is the linear momentum of the child, right? For a single particle, that's how we calculate angular momentum. R cross p. R is like this, p is like this. R cross p is perpendicular out, okay, out of the blackboard, out of the paper, and that's the same as the direction of omega for the rest. So the child and the rest of the platform, the angular momenta for two of them had the same direction. So let's just add their magnitudes up. Okay, so for the child, I now have P, I have L final 1 for the child, okay, is equal to, what is the magnitude of the angular momentum for the child? R cross mv, R and mv, the angle between them, 90 degrees. Okay, so it's just R times m times v is, of course, v1 plus omega r, right? That is the angular momentum of the child relative to a stationary observer measured from this point. What is the angular momentum of the rest of the platform? That is equal to I0 times final omega, the same omega as this. Okay, same omega as this. And I0 is still I0, right? Because it did not deform. So you add them together, what do you get? You get L final equals L final for the child plus L final for the platform. Add them together. Okay, so you have mv1r plus m omega r squared, and that should be equal to L initial. Okay, so let's equate L initial with L final. Okay, then I have I0 omega O equals to mv1r plus m omega r squared. I forgot here to add I o omega. Forgot to do that. So I o omega. Okay, so these two terms, that's for the angular momentum of the child, and this last term is for the angular momentum of the platform. You add them together, that's the final angular momentum, which should equal to the initial angular momentum. And from that, you can solve for the final value of omega. And this is what we get after you solved it. And you see, you have an extra term that we didn't have before. Okay, before we got before was just this result without this extra term. Here's a negative sign, so you get a smaller value of omega than before. So as the child pushes himself forward, the rest of the platform is going to slow down. And that makes perfect sense. Because basically, the child acquires some extra angular momentum this way, and the rest of the, and that comes from the rest of the platform, because the total angular momentum of the child plus the platform cannot change.